Thank you very much, Katerina, for your kind introduction. I have a bit of a cold, I'm afraid, so you have to bear with me. Um, First of all, I'd like to thank very much the ESIS committee and the committee of the European Conference on Fracture for inviting me to give this keynote talk. It's a great honor for me to be here to do that. So thank you. And it's been a fantastic conference and I've enjoyed it very much. I'm the last plenary lecturer for this conference. I'm going to try to keep it relatively light for the end of the conference. It's good to see so many people here after the dinner last night. And I wanted to talk a little bit about some of my reflections on engineering failure analysis, which I realize I've been involved in for 40 years now. And to talk about a few case studies of things that I've worked on through my career. So first of all, I'd like to thank a lot of the people that I've worked with, colleagues at the university and in industry, and also some of the students who I've worked with at QUT in particular, who've worked on a number of the problems that I'll talk about as we go through here. So a bit of an outline of my talk. I wanted to talk a little bit about engineering failure analysis in general, what we're trying to achieve as engineering failure analysts, how we go about it. And because this is a conference that's largely on fracture mechanics, I want to talk a little bit about how fracture mechanics can be used in the process of engineering failure analysis. Some of the advantages it might give us, but some of the pitfalls that need to be looked at as we use fracture mechanics. And then I've got a few case studies that illustrate some of the things that I've talked about as we go through. Failures cost a lot. They cost and they can be very, very disruptive to society. Some failures are small and insignificant, but other failures can really cause a lot of damage. And the costs of failures are really not measured by the cost of the component that failed. When you look at the total cost of a failure, the cost of the actual item that broke is almost negligible as a general rule. It's usually the on costs that really start to cause major financial damage. This image at the top here and below is from an incident that happened on an island off the northwest coast of Western Australia. This was an oil gathering or gas gathering platform. So from a whole lot of offshore gas wells, the pipes came to this island, Varanus Island. The gas was then collected and then sent through a single pipeline from the island to the mainland. In about June 2008, a pipe failed that joined the processing plant or the gathering plant on the island to the pipeline, the undersea pipeline that went to the mainland of Australia. And a fire followed. And that fire burnt for quite a long while because it was very difficult to get anyone to out to the island to put the fire out. And the whole plant was really destroyed, and gas was lost for about 2 months in West Australia. And so the sort of costs we looked at, the sort of costs that were incurred were things like damage to reputation and social license, and the consequential damage, particularly to the environment, but also to the flow-on effects of people downstream who were trying to use the gas. There was an estimate that this fire cost the West Australian economy around about $2 billion. And that's, I think, on the underside of what it was worth. Why did the failure occur? Well, from what I can gather from reading the report, there was a maintenance contract on the plant, And there was a maintenance contract on the pipeline, undersea pipeline, that joined the plant to the mainland. But there was really no maintenance contract on the pipe that joined the plant to the pipeline. And so people forgot about it. And it just gradually, over many years, corroded through and then burst. So it was just purely a corrosion, a general corrosion problem of a neglected item within the plant, and this resulted. I have to say, these are fairly common, silly things that happen which lead to failures. So what does engineering failure analysis do? It's the activity really to try to understand the technical causes of engineering failures. Although I'm usually aware of some of the social issues associated with failures, the causes of failures, I confine myself very much to the technical aspects and let other people, such as lawyers, deal with the social ones. Why do we do it? Well, to prevent further failures, that's the obvious one. To ensure plants operate in control. So if a plant, if a refinery or a mineral processing plant is continually suffering failures, the plant no longer operates under control. It's not in control anymore. And the process engineers will find it very difficult to produce the continued operation of the plant. Addressing warranty issues is fairly common. And what I often do these days is work with insurance professionals or legal professionals to try to address either insurance claims or legal remedies associated with failures. There are other reasons as well, which I won't go into. Next thing is failure analysis an opinion or a fact? And I have to say that after 40 years of working in engineering failure analysis, I think failure analyses are opinions. They're not really facts. And the reason is that we never know all of the circumstances surrounding a failure. We have to read between the lines of the important information that we can no longer get often. Sometimes the part has just been destroyed entirely in the incident. Very often, though, the records that are kept in the time leading up to the failure are very incomplete. So I think it's important to realize it's really just an opinion we're giving, and what we do with the scientific and engineering investigations that accompany a failure analysis is to strengthen our opinion and to test theories and remove certain opinions which don't agree with those experiments. It means also that changes in evidence means that you can change your opinion. And you often have to. You know, if halfway down the track or in a legal case, new evidence comes to light, which changes your opinion, that is fine. Sometimes embarrassing, but fine. This was a failure investigation that occupied me for almost a year. And it was quite a serious incident that happened in Victoria. In 2009, there was a very, very dry and windy patch in Victoria, and the whole landscape had dried out severely. And a series of bushfires occurred in the Victorian highlands. And these bushfires burnt out many, many acres of land and killed a number of people. I think there was about 150 people were killed in the bushfires. A very serious event in Australian history. The fires, the biggest fires, were in two areas. One was called Kilmore East, and the other one was Murrindindi Mill. And these were really the sites of the initiation of the fires. And in both cases, the fires appeared to have been initiated by failures of electrical assets, particularly overhead power lines. After the fires, there was what's called a Royal Commission in Australia, and that means a government-sponsored inquiry into the cause of the bushfires. And after that, there was also a coroner's inquest. which is carried out by the coroner to determine the cause of death of the people. The last thing that happened were what we call two class actions. And class actions are legal disputes from people who had lost loss due to the bushfires against who they thought was the culprit. And I got involved in actually both class actions, and they were both brought against the electric power company. I can't actually say very much about this, unfortunately, because the lawyers tell me I'm not allowed to. Even though the case is settled, and they settled about 10 years ago, I'm still under an embargo as far as talking about technical details, but I can give you an overview a little bit about what happened. The first failure appeared to be related to fatigue of a power line. It was a single steel wire power line that went to a single property. It spanned about 2 kilometers, and we think it might have got struck by electricity and struck by lightning, which then started some fatigue cracks, and the thing failed. It's very difficult to inspect it, and it probably hadn't been inspected for a very long time. It was about 30 years old. The second case was the one that I was mostly involved with, and that is the Murrindindi Mill investigation. In this case, what we believe happened was that there was a modification done to some power lines, which led to one of the power lines breaking during this storm, and then falling onto a barbed wire fence and electrifying the fence and causing fires to spot along the fence line. Now, the witnesses said that the fire started along the fence line. They could see the fire starting along the fence line. And it was on a road to a sawmill. The police decided that the cause of the failure was a slightly strange old man who lived down in the valley near the mill, who was the head of the fire authority, local fire people, and they pursued him relentlessly for 18 months. It was really quite terrible. And after 18 months, they just came to the conclusion that it just couldn't have been him. And they really ruined his life, fortunately. So after that, they turned their attention to the electrical assets. As I say, I can't say too much about the technical details of the thing, but despite there having been a Royal Commission and a coroner's inquest, we found new evidence. We found some new evidence in our investigation. And although the electrical power company denied any responsibility for this, on the steps of the court on the day that the trial was supposed to start, they decided to give my clients around about 200 million euros in order to settle the claim. So that all went away. Just to give you some idea of scale, these red areas are the areas of the fires, the two fires, Kilmore East, Murrindindi Mill. Victoria is around about 4 times the size of Croatia. It's about half the size of the UK. So it's quite a large amount of area that actually was burnt. All of those red areas burnt on this day. And unfortunately, bushfires continue to be a major problem for Australia. So the failure analysis process really involves a number of things. Evidence gathering is key. We need to gather evidence. We need to develop some hypotheses, and then we need to do some experiments to test those hypotheses and possibly do some modeling. And it is all to try to develop an opinion which we can support with the experimental work. So the synthesis of theories requires testing the theories against whatever evidence we can gather. what I like to do then is to compare the existing knowledge, compare what I see with the existing knowledge. As Katerina said, I started investigating failures in about 1985. First failure I looked at was a shaft. I think it was a spline shaft. They fail by fatigue in a particular way. And I worked as a professional failure investigator for a few years. What I discovered fairly quickly was that I knew nothing. We relied very much upon things like this ASM handbooks as our guidance, but they're quite limited in the end. One day, one of my colleagues brought a computer into the laboratory. He had bought a personal computer. And I knew at this stage that it was possible that computers could be connected to one another over a long distance. Pardon me. And I thought at that time, wouldn't it absolutely be marvelous if we could connect computers to a database of engineering failures that we could search through and look at and see what other people have done in the same sort of circumstances when they investigated failures, so we could all learn off one another. To my surprise, many years later, I had the opportunity to actually develop exactly such a database. And this became a big part of my life for about 12 years. And I still use it a lot. And if you're faced with doing engineering failure analysis professionally, I really recommend you start to use some of these things like engineering failure analysis. Thanks very much, Goran, for giving a good plug in the last talk to engineering failure analysis. Sorry about my cold. Right, how do I look at failures? I look at it in terms of three possible reasons for the failure: design, manufacture, and use. And usually it's one or more of those. So for design, I'm looking at everything that was the responsibility of the design team. Did they do the right things? For manufacture, did the manufacturer actually execute the design that they were given properly? Or were there manufacturing defects within the component? And use, everything that was the responsibility of the end user. Was it being used correctly, or was the failure directly attributable to maluse of the components? And so whenever I'm looking at a failure, these are the things that are going through my mind as to where we should be considering looking for the improvement. A few years ago, the process of failure analysis that I described before is a fairly standard one. But a few years ago, a few of us decided to look at methodologies of failure analysis. It was spiked by a student, Nigel Booker. And what we did was we looked at all of the failure investigation cases described in the small journal Case Studies in Engineering Failure Analysis, and tried to identify different methodologies that were used. I'll just give you a little bit of an idea of this, but I don't want to spend too much on this. The first one, empirical statistical diagnosis, covers what I described before, which is evidence gathering, synthesis of the evidence, and then try to understand the failure. But there are a number of other ways you can tackle failure analysis. In the set-based diagnosis, what you can do is look at statistically a whole lot of tests that examine the failure and gradually narrow down the tests to eventually describe what the failure is. Experimental diagnostics is usually where we try to absolutely simulate the failure, try to simulate exactly what happened in the process. Case-based reasoning is where we just look at different case studies and try to compare the cases to the failures. And model-based diagnostics is more about doing simulations, finite element analysis, other types of simulations to try to understand the mechanics of the failures. Overwhelmingly, we found most of the failure analyses in case studies in case studies in engineering failure analysis were of the first type, empirical statistical diagnosis. But there were some other examples as well, examples of the other techniques as well. The other things we started to look at were what sort of things influenced how people chose the methods of investigation. And Nigel looked at where the authors came from and used the Hofstadter characteristics of countries to try to look at how risk averse and how the different personality type characteristics of what we would expect for the investigators, and whether we could find any strong relationship to how they chose the methods of investigation. We used principal component analysis and looked that the main factor appeared to be indulgence versus restraint as a characteristic, whether conservatism versus a bit more adventurous type approach. Uncertain people who were the other principal component that was important was mostly around uncertainty avoidance, with people depended how certain people needed to be of the solution. And the final principal component was the industry score. Right. I want to go through, I won't talk too much about fracture mechanics because I think we all know mostly about what's going on. I just put up this quote from 1959 conference that brittle fracture became a matter of great concern in about 43, when in World War II, the shipbuilding program was in full swing. Early investigations of this committee showed that the problem was by no means straightforward, as some people had thought. I think that's fair to say about fracture mechanics. But the key issue about fracture mechanics and its use is that we want to be able to join together the ideas of loading, the material type, and the crack size. If we know two of those, we should be able to tell the other. So in theory, fracture mechanics should be able to be used as a tool in failure analysis. How useful is it in practice? Well, my experience is that fracture mechanics is not used terribly much in routine failure investigations. It's only fairly specialist stuff where it's used. A number of possible reasons why. It's fairly complicated, it can be expensive, and the technical capacity of investigators is not always there. This is improved with things like standards such as BS 7910 and API 579. I have used fracture mechanics to some extent. They're usually as sanity checks or as determining upper and lower bound solutions to problems. And I'll give you a couple of illustrations of that if I've got a bit of time. I've got 3 case studies. The first one's a shaft failure. It is a fracture problem, but it's not, the root cause of the failure is not a serious fatigue issue. It was a step shaft in a refinery. It was a high-speed shaft. It had just been remanufactured and heat treated, returned to the refinery, and it broke after only a few hours of operation. Definitely a short-term failure. And it failed right at that point, which I thought was really odd because that's the thickest part of the shaft. Why would it break there? There's no change in cross-section. When I looked at the fracture surface, it was a fatigue failure for sure. You should be able to see some beach marks delineating the crack propagation. what I did was on this shaft here, which there are several shafts. This is an intact shaft. We did some mag particle in just this area and discovered the whole thing was cracked. And then I did a little bit of differential etching and found a large patch of white etching material here, and it was associated with the cracking. This was an example of stupid things people do. What I think had happened was that when they heat treated this shaft, they didn't check the distortion, and it was distorted when it came out of the heat treatment bath. And this was heat treated and nitrided. The guys then discovered right at the very end that it was distorted. So what do? They got an oxy torch and they put an oxy flame onto the surface in order to try to expand it and get the shaft back into some kind of undistorted shape. And then didn't check it before they put it back into service. So yes, stupid things people do. It was a fatigue failure, but probably not a lot of science in that one. This was a little bit more interesting. These were a series of high tensile strength cables, which were used to hold in anchors on a foundation. This is a building foundation. So these were put in, they were loaded up to the required amount. 2 days later, they broke and the foundation fell into the sides of the foundation fell in. Couldn't really understand why. The steel was a typical high tensile cable steel. And when we did magnetic particle testing on the wire, I don't know if you can see it, but there are many, many, many tiny little transverse cracks all the way through that steel. And when I looked at a micro, what we saw was stress corrosion cracking cracks, and they came from pits on the surface. Now, one of the questions that I was interested in was, had this been overloaded? Was this overloaded at the time that it failed? So what I did was a fracture mechanics analysis of the defect sizes. We knew roughly how big the defects were, maybe a little bit more. And I I got a fracture toughness from the literature. That's about all I could do. Couldn't do any more than that. And we knew what the tensile strength was of the material. And I evaluated it using a failure analysis diagram. And I found that the critical crack size for failure was about 0.45 of a millimeter. Now, the cracks I showed you before were up to about 0.3 of a millimeter. It seemed to me quite feasible that the worst crack there could have been 0.5 of a millimeter. And therefore, I didn't really have any evidence that this was overloaded. I thought it was probably failed under normal conditions. Why it was failing by stress corrosion cracking, I don't really know at this stage. I might not be good. Can I go? Is it? All right, okay. Fracture mechanics, this was a sanity check, really. So why did the SCC occur? I'm not really sure. The environment was exactly the same as that always used before. We don't really know the history of these wires, so we were struggling a bit there. The other thing is, what was it overloaded during installation? I wondered about that. Couple more case studies I'll go through quickly. And this is really about fatigue life and remnant life and inspection intervals. It is possible theoretically to determine inspection intervals from a fatigue analysis. It's not always easy, but it's very useful for setting NDT programs and non-destructive testing intervals. I was presented with this failure. It's an absolutely beautiful fatigue fracture, at least for people like me. And not so beautiful for the mine. It was from a drag line from a mine. The actual cause of failure is pretty obvious. there's a oil gallery here or a grease gallery here, and the crack started at the grease gallery, probably just on the inside, and then grew through. This was about 40 years old, this pin. For almost all of its life, the technicians who maintained the pin were told that when they pulled the pin out, the orientation of the pin when it went back in had to be such that the oil gallery was on the neutral axis of the bend of the pin. These technicians, for some reason unknown, decided they would put the pin back at 90 degrees so that the oil gallery was on the tension side of the bending of the pin. And so that hole up there creates a stress concentration of about 3 times, and that was sufficient to cause the fatigue. If they'd always put the pin in the correct way, the pin would probably never have failed. The question I was asked was, they said that they did non-destructive testing of this pin by using ultrasonics from one end, and they did it at every 6 months, every 6-month interval. And they said, should this have been picked up at the last 6-month interval? This is a big crack. Instinctively, I would say yes. But could we get some estimate of how fast the crack would grow using fracture mechanics to justify that? Well, the pin was in a clevis like this, and the clevis, the pin would sit in that clevis, and a force was applied to the pin through a wire rope. And the crack grew around about there. And I used three methods to try to model how the stresses would propagate through this pin. I didn't use finite element analysis. I just used Excel spreadsheet. That's all it needed. The first was to assume that the pin was a simply supported beam. That is, there was no moment restraint at the ends of the pin, and it was free to bend. The second method of analysis was to assume that the pin was in castra at both ends, that it was fixed. And that's probably closer to the truth because there were plates put on the end of the pin which were meant to stop it from rotating. But that's never perfect, and the sides of the clevis would also deform a little bit. And so a third analysis was done was to change the degree of compliance at the ends of the pin. So for the Encastra method, number 2, the model looked a little bit like what I've drawn on the left side. The only difficult bit of this was actually to work out the compliance of a cracked pin. And I used a lovely paper by Professor Toribio to help me there. In the simply supported case, we had the moment was constant throughout the pin, and therefore, as the crack length increased, the stress intensity increased, as we would expect. And so, as the crack grew, it got faster and faster and faster, and eventually would have broken through. I don't think that's what we saw on the fracture surface. The fracture surface is telling me something different to that, because the fracture surface was actually almost entirely through the pin before it actually broke. But in the case of the simply supported beam, I could estimate the fatigue crack growth rate using that fracture, those stress intensities, and I got that curve there. If I look at the Encastra support, where the two ends are fixed, as the crack grows, less and less of the load of the component has been carried by the crack. And so what we see is that in the red graph, as the crack increases, the black graph says that the moment at the crack will decrease, and the stress intensity range goes up, peaks, and then drops again. And so what we see is a crack grows, it gets faster, faster, slows down, and then theoretically might arrest. I've put the, I modified that Encastra by modifying the moments at the ends of the pins, and got 3 different fracture crack growth rate curves. should the crack have been detected? I knew what the forces were roughly on the load, and I knew that there were about 4 cycles a minute. And so I estimated that there was a rate of about 720 cycles per day on the pin. In the simply supported case, that was the worst case, which I knew wasn't actually true, but I knew it was possible. That was as fast as it was ever going to go. The crack should have grown from about 25 millimeters to 150 millimeters in about 450, 460 days. In the fully Encastra model, it was about 16,000 days. And in my best estimate, it was around about 2,600 days. Now, the reason I said 25 millimeters to 150 millimeters is, the reasoning is this. I figured that not even the stupidest NDT tech could miss a 25 millimeter deep crack. I shouldn't say stupid. Even the most careless NDT technician should be able to detect a crack that is 25 millimeters deep. And 150 millimeters is the limit of what the equations would work for this particular setup. And I thought any crack that's bigger than 150 millimeters is going to crack really quickly anyway, so it doesn't really matter. So the answer really was the crack should have been detected 6 months ago. It should have been detected, and the NDT company had a few questions to answer. The people on the mine site were worried that their inspection methods were not correct, but I think this sort of showed that their inspection intervals were about right. I have another case study, but I'm not going to do it because I think I'm out of time, aren't I?
Yeah.
Okay,
Slowly.
so thank you very much.